Hello everyone and welcome back. We have been exploring the fascinating Cayley-Hamilton theorem and its application in finding powers of matrices and their inverses. Today, we are going to take it a step further and see how this theorem can help us evaluate polynomials of matrices even when the degree of the polynomial is quite high. This can save us a lot of computational effort. Just as a reminder, the Cayley-Hamilton theorem states that every square matrix satisfies its own characteristic equation. If T of lambda is the characteristic polynomial of the matrix A, then T of A is equal to the zero matrix. Let's consider the 3 by 3 matrix A given as follows. Our goal is to evaluate a polynomial in A given by a raised to 5 plus 7a raised to 4 minus 9a cube minus 8a square plus 15a plus 4i. Let us first form the matrix A minus lambda I, where lambda is the eigenvalue and I is the identity matrix of order 3. This is going to be minus 1 minus lambda 1 0 1 2 minus lambda 1 0 1 and 1 minus lambda. Our next step will be to set up the characteristic polynomial. The characteristic polynomial is given by C of lambda and it is equal to determinant of A minus lambda, which is the matrix we have just evaluated above. So it is going to be minus 1 minus lambda times the minor, which is 2 minus lambda times 1 minus lambda minus 1 times of 1 into 1 minus lambda minus 0 and plus 0. This is equal to minus 1 minus lambda, and we can simplify this to 2 minus 3 lambda plus lambda square minus 1, and this simplifies to minus 1 plus lambda, which gives us minus 1 minus lambda. 2 minus 1 is 1, so we have 1 minus 3 lambda plus lambda square minus 1 plus lambda. Let us multiply these two terms and we get negative 1 plus 3 lambda minus lambda square minus lambda plus 3 lambda square minus lambda cube minus 1 plus lambda. Now the highest power is lambda cube, which is here. So we have minus lambda cube followed by the quadratic terms minus lambda square and plus 3 lambda square, which gives us 2 lambda square. The linear terms plus 3 lambda minus lambda and plus lambda, which is plus 3 lambda. And lastly we have minus 1 and minus 1, which gives us minus 2. So this is the characteristic polynomial of the given matrix A. Let us apply the Cayley-Hamilton theorem to our matrix A, and by it we know that C of A must be equal to the zero matrix. That is minus a cube plus 2 times a square plus 3 times of a minus 2 times the identity matrix is equal to the zero matrix of order 3. Coming to the question part, we wish to evaluate this expression. Let us call this polynomial as g of a. So g of a is given as a raised to 5 plus 7a raised to 4 minus 9a cube minus 8a square plus 15 times a plus 4 times of I. If we replace a by lambda, we get it as g of lambda is equal to lambda raised to 5 plus 7 times lambda raised to 4 minus 9 lambda cube minus 8 lambda square plus 15 lambda plus 4. Now we have got two polynomials. One is g of lambda whose degree is 5 and another one is c of lambda whose degree is 3. So we can think of applying the division algorithm wherein we are going to divide g of lambda by c of lambda. The first quotient is going to be minus lambda square. So we get here lambda raised to 5 minus 2 lambda raised to 4 minus 3 lambda cube plus 2 lambda square. After subtracting, we will be left out with 9 lambda raised to 4 minus 6 lambda cube minus 10 lambda square. We'll bring the 15 lambda down, so plus 15 lambda. The next coefficient is going to be minus 9 times of lambda. So this is going to be 9 lambda raised to 4 minus 18 lambda cube minus 27 lambda square plus 18 lambda. Again, subtracting gives us, we get rid of lambda raised to 4 term. Here we are going to have 12 lambda cube plus 17 lambda square minus 3 lambda. And lastly, we will get the plus 4 down. The next coefficient is going to be minus 12. So here we have 12 lambda cube minus 24 lambda square minus 36 lambda and plus 24. And subtraction here is going to give us, we'll get rid of the lambda cube term. Here we get 41 lambda square plus 33 lambda minus 20. So using the division algorithm, we can say the dividend, which is this, which we had called as g of lambda. So we have g of lambda is equal to the divisor, which is this, that's our characteristic polynomial. So c of lambda times the quotient. The quotient is the quadratic polynomial here. So times minus lambda square minus 9 lambda minus 12 plus the remainder, and the remainder is this quadratic polynomial, 41 lambda square plus 33 lambda minus 20. If we replace lambda by a, we are going to get g of a is equal to c of a times minus a square minus 9a minus 12 times I plus 41a square plus 33a minus 20. And by the Cayley-Hamilton theorem, we know that c of a is 0. So c of a multiplied by this quadratic polynomial in a will be 0. So g of a reduces to only 41a square plus 33a minus 20i. We now want to evaluate a square. So a square is going to be a times a, and that is 2, 1, 1, 1, 6, 3 and 1, 3, 2. And therefore 41 times of a square is going to be 82, 41, 41, 41, 246, 123, 41, 123 and 82. Then next we need 33a. So 33a is going to be minus 33, 33, 0, 33, 66, 33, 0, 33 and 33. And lastly we need 20i. So 20i is going to be 20 on the diagonal and non-diagonal entries 0. So we have g of a is going to be the 3 by 3 matrix. So we have 41a square, the first entry is 82 plus 33a, that is minus 33, and minus 20, which is 20. So we get the entry to be 82 minus 33 minus 20. The next one is going to be 41 plus 33 minus 0. And all this reduces to, thus we can conclude that a raised to 5 plus 7a raised to 4 minus 9a cube minus 8a square plus 15a plus 4 times I is equal to the 3 by 3 matrix which we have just obtained. Now it's your turn. Try evaluating the polynomial h of a is equal to a raised to 4 minus a cube plus 2a square minus 3a plus I for the same matrix A. Share your answer in the comments below. As you can see, the Cayley-Hamilton theorem provides a systematic way to evaluate polynomials in matrices even for high degree. This is a powerful tool in various areas of linear algebra and its application. If you found this video helpful, please give it a thumbs up and subscribe for more linear algebra tutorials. Don't forget to try the example problem and share your answers in the comments below. Let me know if you have any questions or suggestions for future videos. Thanks for watching and happy learning.